In this lesson, we're going to be talking about one of the really big ideas of linear regression, which is called correlation. So first of all, I had students enter in digits 0, 1, 2, 3 through 9. And so they entered 10 one-digit numbers. So they did 10 digits. And then they did 20, 30, 40, 50, etc. And we timed them. And we checked to see if there was a relationship between the number of digits they were entering and the time it took. So here's the data for one of my classes. When they did 10 digits, it took them 7 seconds, then 9, 15, 16, 20, and 26. Now, I'm going to go ahead. If you recall when we visited frequency tables, you might notice some similarities between what we did before and what we're doing now. So I'm going to go ahead and calculate the deviation of X from the average. Now, the average for this should be pretty easy to figure out. Oh, it looks like it's halfway between these two because it's nice and evenly spaced. But to be sure, I add this all up, divide by 6, and I get 35 digits. It's the average. And I can go ahead and calculate the standard deviation for the units as well. And that is the spread is about 18.71 digits. So on average, the digits are about 18 digits away from 35. Okay, then I'm going to go ahead and do the difference. Remember, this is the X value, and go X minus the X average, which is this column right here. 10 minus 35 is negative 25. And I keep doing that for all of the X values. Since these are very regular, you can definitely see the pattern going on here. Now, the Y pattern, there's definitely a pattern. It's increasing as the number of digits increase, which is totally logical. But it's not quite as regular. And I'm going to go ahead and calculate the Y average, which is adding all these up and dividing by 6, because there are 6 data points there. And then I can also find the standard deviation, which is 7. So most of this data varies by about 7 seconds from the mean. Then I go ahead and subtract those two and find the deviations for Y. Okay. Now, if before, when we're doing standard deviation, we would square this, add them up. But instead, what we're going to do now is we're going to multiply these two products. And when I multiply these two out, these are the numbers I get. I have negative times negative is positive, negative times negative is positive, etc. Okay, well, now we're going to be looking at a formula for a correlation, which actually is 1 over n minus 2 times x minus x bar times y minus y bar. So we've kind of looked at this, when we add these up, we're looking at this sum here. And believe it or not, you can calculate correlation using this formula, although we really won't. It's much easier to use technology to do it. But this is sort of like what we're doing before with standard deviation and variance. But it behaves differently, and let me show you how that is. So I went ahead and graphed the data on my calculator. Here I'm going to go ahead and put the graph, and this is actually my calculator screen. I overlaid it. I'm so clever. And we said the direction of this scatter plot was positive. Now the question is the product of these deviations positive or negative? So first of all, I'm going to mark the point where the average is. It's right about there. And in fact, I'll draw a horizontal line right through it and a vertical line right through it. So if an X value is to the right here, to the right of this vertical bar, it's above average. If a Y value is above this line, it's also above average. Below average is on this end for both, and above average is on that end for the both. So is this product, the difference between the point and the X coordinate and the X average and the Y coordinate and the Y average, positive or negative? Well, you can see that it's positive. When X is above the average, so is Y, which means these are two positive numbers, so it is greater than 0. How about when X is below average? Well, okay, so that's going to be negative, this product, and so will that be negative. Negative times negative is positive, so this is also greater than 0. What that means is that we have this positive association. We tend to get mostly positive products here. If I had a negative association, I would get negative products. Let's go ahead, and what was the form? We agreed it was linear, and the strength seems to be pretty strong. And I'm about to show you how we can measure strength using correlation where we can be specific. So when we're trying to do correlation, what we're trying to do is figure out which line would fit the best. Now, I'm actually showing you something called a residual. So if one thing I could do, let's say I had all these values and I wanted to predict what the average Y value was. Well, I could just actually use the average Y value, which is represented in this point right here. In fact, if I adjust this, you can see the average value changes. So this point represents the coordinates for the average X and the average Y. But you're probably thinking, oh, you could do better than that, because if if X is high in this case, Y is low. I should be predicting below the average value. If X is low in this case, Y is high. So let's go ahead and do this. I'm going to adjust this line until I make these residuals hopefully as small as possible. This seems more like the line I would want. Now, I do have a way of turning on the actual regression line, and I'm pretty darn close to it. And you can see that this is a very negative regression, all right? This is called the correlation, which is R, and it measures the strength of the correlation. In this case, if I were to put these points, let's go ahead and line them up all on a line the best we can. I'll just move them to my line that said move this. All right, so I'm just trying to put all my points on that line the best I can. Here I got -1. Now that doesn't mean that the slope is -1. What it means is that it's perfectly correlated, or almost perfectly, there we go, so that if I go down one certain way in X, then I go down the same way in Y. That's, again, not to confuse it with the slope, because the slope here is -0.4. And that would say for every increase of 1 unit in X, I would go down -0.4 in Y. What this correlation means is, think of it almost like a percentage, although it's not quite. It means that we are all our change is explained by this line. Now, can you have positive correlation? Sure. So let's go ahead and adjust these. And what is this biggest value of ours? Well, you'll notice I'm kind of messing with the dots now. And if I look at it, my R is getting very low. So how strong is this equation here, or this linear form? It's not very strong. In fact, if I make a nice little circle with the whole thing, like I just sort of have some dots around, it gets pretty darn close to 0. So the closer this is to 0, the weaker the strength. All right, now we're going to go ahead and make this some more of a positive correlation. So it doesn't matter which points you have where. And I'm going to try and make this perfect. So tell you what, I'm going to try and line up. Come on. I'm going to try and line up perfectly here. So this C is going to get on my line, and this A is going to get down on my line. And that's pretty close. Come on, B. There you are. All right. Oh, the strongest I could make this, and here, let me move the equation so you can see it, is a value of 1. So strongest correlations, and I'm going to go ahead and do this again with a steeper slope. So my slope is, not worried about that label, trying to get everything beautiful. And you can see that, again, I have a different slope this time, 0.72, and my correlation is still 1. So the correlation is just how well the X value predicts the Y value. It is not the same as the slope. And we do have some ranges that we can use to determine the strength of the correlation. So we do have some guidelines. Okay, so first of all, what was the form and strength for the largest possible value of R? It was 1. And the form was very, very linear, and there was a strong positive association. For the most negative value, that was -1. It was still linear, and that was a strong negative association. Is R the same as the slope? No. The correlation just measures the strength of fit and kind of the direction. Slope measures how much y changes with 1 unit change in x. And I will actually be in the next lesson talking about how to interpret that. But it pretty much comes down to this sentence, which is how much whatever your response variable changes with every change in our explanatory variable. So here's a guideline for values of r. And, you know, there's some variations, but this is one I ran across. Here, if r is less than 0, hopefully you notice that the slope was negative. If r is greater than 0, the slope is positive. Now, the strongest fits we saw were at -1 and 1, so we would put strong on both of those ends. Between these two, we're going to say it's, well, when the weakest we saw was 0. And in between, we'll say, it's moderate, okay? Now we're going to try and match the images here to these different correlation values. If I have a negative here, that needs to be a negative slope. So it's either this one or that one. But it's -0.928. Is that in the strong, moderate, or weak? That's definitely in the strong area. So I would put it on this one, which has a much stronger linear fit. -0.411 is also the negative slope, so it's probably this one. And that's kind of in the weak area, which kind of fits the pattern that we're seeing here. 0.002 is very weak, and it could be positive or negative, and we're going to say that that goes with this picture right here. And then finally, 0.711, well, that's positive slope, and it's almost as strong as this one going in the positive direction here, so it would be this image right here. So one group was late, and they gathered their own data for the Barbie bungee jump. How safe do you feel Barbie's bungee jump would be if we use this data? So here it is, and I'll go ahead and show you the scatter plot that they get, which should match the one that's already on your notes. So my explanatory, and put in my numbers. And one thing I'm going to do here is that the Statplet will actually also calculate correlation for you. So you hit begin analysis like before. Now if you come down, calculate correlation, our correlation is quite strong. It's 0.992. So how comfortable would we be? There's a very strong positive association between the number of rubber bands and the distance, and r equals 0.992. It's very close to 1. All right. So one of the members stuck some extra rubber band, snuck some, not stuck some, to collect more data. And he found when he had 15 rubber bands, the Barbie went 49 inches. So if we add this point to the scatter plot, how does this affect our correlation? Does this lie along our line, or is it kind of pulling off the line? Well, it actually makes it stronger because it does follow our line. And when I add that data point in and hit the correlation, calculate, it gives me 0.998, which is even stronger. Now, another group member did his own measurement, and he accidentally left off a digit, and he said, oh, 6 rubber bands is 6 inches. So when we put that point there, how does this outlier affect our correlation? Well, it doesn't follow the line, so it's going to make it weaker. In fact, it lowers it all the way to 0.838. So we also noticed the group didn't follow the directions. They were doing inches instead of centimeters. We converted all those inches to centimeters. And how does that affect the R for our new set of data that's now in centimeters? Well, if we go ahead and enter all the data points, so 0, 1 through 7 for rubber bands, and now we put in our centimeter data, is that really going to change the shape of the scatter plot? Well, hopefully you'll notice that it's just going to change the scale. It's going to look very similar to our first drawing. So I'm just looking at the original set of data, and then when I hit begin analysis, there you go, and calculate correlation, it's pretty much the same. So R for my new set of data is 0.993. Now, let's say you want to get correlation on ClassPad. So you start a new sheet and click on data up here, just like before. Enter your data in 2 columns. X values or explanatory variables need to be in the first column and Y values in the second column. Highlight both columns and you get this window, and then you're going to click, instead of graph or calculation, we're going to click on regression. Then you're going to get this window pop up, and you want linear regression, which is right there. There are other types of regressions you can explore, but for our course, we only do linear regression. Remember that correlation is signified by R, so you can see there's our data, 0.99299, really 0.993 for our data, and that's how you can find correlation. If you're using your calculator, there it is. If you're using the TI-84, there's this annoying thing with the TI-84. If you do not have diagnostics on, when you do the calculation, these 2 lines will be missing. It will only show you these 3 lines. So we make sure it's on by pressing second and then this catalog button right here. Scroll to diagnostics on. You can just hit whatever's D, the green D button is, and that will get you to diagnostics on right here. And it might take you a while to scroll, and then press enter. Then press stat like we did before. In this and calc, so we're in this tab where we did our 1var stats, except we're not going to do 1var stats this time. We're doing number 4, which is Linreg, linear regression, AX plus B, and you press enter. By the way, make sure you have enter. This is what you enter here. So X list is list 1 for us. Y list is list 2. We almost never deal with the frequency list. If you really want to graph the line, you can do vars and pick like Y1 there, but that's not really necessary. Then hit calculate and press enter, and you get this screen. The correlation coefficient is R, which is this value right here, and you can see that matches what we got on our other software.